About what we're doing at Continuum. We've been kind of doing a lot of things, building the team, organizing together, all around really trying to take Python to the next level of big data processing. What I've noticed is a lot of people are using the Python stack, including NumPy and SciPy, to analyze data and to do it on a big machine. And then I hear a lot, in fact, a lot about this great thing called Hadoop out there that's supposed to solve everybody's problems if you just change everything you're doing to a MapReduce framework. And, and then you look into more detail and you realize, and that really means store all your data in HDFS as text files and then go through and do text processing all day long every day. I'm thinking, wait, I stopped doing that, like 20 years ago. That's why NumPy exists, so you don't have to be processing text all over again, over and over, all the time. It's interesting, though, to see when you go to one of these conferences that go talk to people about what they're actually doing, and they're using Python behind the scenes. And they say, you hear a lot, I'm prototyping in Python, then I have to deploy to a Hadoop cluster. So that's, the people are using tools like NumPy and SciPy, and then you look at what's happening in the scikits world, the scikits learn, scikits stats model, scikits image. There's some great things happening, really exciting developments. Pandas is coming out and making it very easy to manipulate all kinds of data very quickly. The IPython notebook, all this stuff looks cool, and then it feels like we're all going to be doing it in Java if something isn't done. There's so many areas for big data, I'm not going to go down that list. Today, people are using Python for big data, so how do we help them? How do we make that easier? And then go from there to actually fixing some of the issues that are actually at the root of it, NumPy, that make it hard to do things like delayed computation, additional column storage data types, derived column data types. How do you fix some of those fundamental issues? The visualization stack, improving that. How do we get around from people saying, I use Python NumPy every day and then move to Java, move to Hadoop? So at Continuum.io, we're trying to change that story. I'm going to start a little slideshow running. I don't have much time, unfortunately. There's a little video that's actually running right now, which explains a little bit of what we're doing. It's too long to me to show. It's 10 minutes, but you can go find a link.
I'm here to show you CDX. CDX is the Continuum Data Explorer. And we made CDX to make it easier for people to interact with, visualize and analyze data, and to do so collaboratively with their peers. The first thing that I'm going to do is load some data into CDX. I have my CDX backend pointed at two groups of data. The first is data that resides in Disco. Disco is a Python and Erlang-based MapReduce framework. And Disco comes with DDFS, which is its distributed file system. In DDFS, data is organized into tags, and each tag points to multiple files. This tag points to one file, and if I click it, I'll load that array into CDX. So I get a summary view of everything that I loaded into CDX, and here I get some metadata about the array, and I get some summary statistics for each of the columns. When I load this array...
Okay, like I said, I can't explain all of that, so I'm going to have to stop. But you can basically load data. This is something we're going to come out with in a little while. It's a preview of some of the work we're doing to make it easy to explore large data sets and interact with them through a web browser in collaborative exploratory data and analytics. I wanted to point out our website's changed. It's a new launch. Some of the important things to feature here are what we're doing, what we're about, what we can do for you. And then also, I want to point out this community edition of Anaconda. Anaconda is a Python distribution for large-scale data analytics. It's basically all the wonderful packages you're used to pulled together and for server-side processing. There's several downloads here. You can go get a Linux tarball that'll work on multiple platforms. You can get a VM to try things out on Linux or OS X if you'd like, or on Windows if you want a VM that has everything installed you need, or there's an AWI file that lets you run on Amazon. So that's what we're about. There's all kinds of things going on, ways to get involved. There's developer resources, and also here you can learn more about the projects we're doing, some of them we talked about here, Blaze, Bokeh, and Numba. And all of this is for data analytics, large-scale data analytics, and to fight against the Hadoopla. Thank you.
Chris Cope. My name is Chris Cope. I'm with Resilience Science, and I stay awake every night thinking about big data. I completely agree with pretty much everything Travis just said. There's this scary big data thing that everyone's thinking MapReduce is the answer to. Now, when people say big data, what exactly are they talking about? Are they saying is 10 terabytes big data, 100 terabytes, a petabyte, 100 petabytes? Here's what I think. This is what I call my big data graph. It's all about the trends. And you look back 30 years and you see you have the growth of data, compute power, Moore's law, and then the lesser known Nielsen's law, right? Moore's law only covers CPU, processor growth, processor power. There's this other one which covers, the growth of network bandwidth. So you look at this and you see something very, very scary right here, which is that the past 4 or 5 years, there's this inflection point where data growth is growing not just exponentially faster than everything else is growing, but it's the second derivative is also growing as well. So you look at this and you're an HPC big data person like myself, and you think, well, what does this mean? This means a couple things. This means that the way we used to do things won't work anymore. The difference between the data size of data and Moore's law means that even with advances in processor design, our runtimes will grow exponentially, and unless you make everything massively parallel. And you can't move data across the network anymore because the data is going to get too big. You already have, half a petabyte genomic data sets. Just a single data set's half a petabyte. You can't move that from one research group to another research group. So, and this is, that's a little hand-wavy graph. I'm just trying to, aggregate this data growth trend. Here's where you see it everywhere. You see it in biology. This upper left picture was published in Nature last week. The one below that is one from NIH, and that sort of shows why data is growing faster and faster than it was before, is because it's getting cheaper to produce that data, and the data is getting more useful. So we're spending more money to produce data that's so much cheaper to produce than the year before. The upper middle is, data is outpacing storage growth, which is why the upper right, astronomers are paying more money for the same data that they've been getting, every year. And then you see this, Verizon sees this and Cisco sees this across the board. So what does all this mean? I think there's 3 clear answers of how we can keep doing large-scale analytics. One is everything has to be massively parallel, everything. Even if you don't consider your job to be HPC, it's going to be, because the sheer volume of your data relative to the compute resources you have is going to grow. 2, you got to send everything to the cloud. And I know everyone likes to, thinks the cloud's like a big buzzy, a big fluffy buzzword, but the great thing about the cloud is that, especially for scientists, it's a collaborative platform. You share your data, you share your software. Number 3, it has to be easy, it has to be simple. Everyone's talking about how we can use Python to do implicit parallelism this week, and I think that's great, especially because not only is it going to be very hard to write these very massively parallel codes, but the developers who are going to have to write codes like this are engineers and scientists who don't have the same background. Now, if only someone would implement something that would implement take care of those 3 things and aim it towards domain scientists. So Jon Riehl gave a talk yesterday. He worked on Numba and he developed Riehl, which we open sourced a version of yesterday on GitHub. And yeah, basically it's implicitly parallel. You write this very, very high level, model. So to run through it very quickly, go to the website, create a new job, enter your Riehl code. The Riehl code, by the way, is so much smaller and denser and easier to write than the old code. Click run. Run it on 301 cores because it's more than 3,001 cores. And it runs at 344 times faster at the click OK button. Data is no longer scary. Thanks.
Thank you. My name is Matt McCormick, and I work at Kitware, and we're hoping to have a better presence here at the conference here next year, sponsor. But I'm going to talk about my favorite things. Let's start with C today, some of my favorite things. One of them is Cython. Cython is excellent for speeding up your code and also for bridging to C, C++, other libraries out there that you've written or you just want to use. So that's very fun. And Python is really great. As many people have said, it's dominating as this super glue and this integrating language, this lingua franca for scientific computing. So that's awesome, but in my experience and what people have said, like at the astronomy mini symposium, we need work on building and installation. That's still really a weak point. So one of my other favorite things is CMake, which is an open source package. It's cross-platform, and it's made for scientific software, but it's used all over the place for building C, C++, and Fortran code. And it makes building suck less, as someone said. So I've just been playing around with this. This is just a toy that it's on GitHub. You can clone it there and try it out. It's nothing that's official yet, but this is how it would work, or it does work right now. So it's the code is here. Here's my code repository, and inside the repository I have Python code, and then these pxd files, and which are Python, and C or C++ header files, and then there's the CMake scripts that are used to specify the build. And then from these CMake scripts, we can run a build, and we can generate makefiles on Linux or Mac, or Visual Studio project files, etc. on Windows. And we have a nice clean separation of our build tree. So this is a different directory than from our source tree. And let's try a live demo. So there's a CMake executable, an ncurses interface, a GUI text file, and then we pass in the source directory. I can't quite see here. Okay, let's go to a different directory. That's a little closer. Okay, pass in our source directory, and it's going to detect our compiler, and it can find libraries for you, and you can configure libraries. Maybe you have Python in a different location. You maybe have a different Python build that you want to link with. Okay, so these things can be done. And it generates some nice color make files for you. And this is just a simple example, is calculating pi in an inefficient way. In pure Python and Python, and the first one is Python. It happens very quickly, and in pure Python, it's slow. So there's an example. You saw how it works. There's many other nice things that are available with this, but I encourage you to take a try and give some feedback if you have time. Thank
you. My name is Mark Moulton. I have my own consulting company, Pythias Consulting, and I work for a company called Educational Data Systems in California. I'm in the field of psychometrics, and which I haven't seen anything like that in SciPy yet. This is my first time here. But it has a very fundamental and interesting problem, and I've written software around that problem. And I think you'll find it interesting. The software is called Daemon. The idea is this. You want to measure persons' mental traits, and you need to do it in a way that is utterly reproducible. It's almost a legal requirement. In other words, if you give a test to a certain set of kids, and then you give those a different test to the same set of kids, you need those kids to be completely comparable regardless of the test questions they have taken. That's the main problem of psychometrics. I wrote a program called Daemon to generalize this problem to multidimensional spaces. It's kind of a mixture of machine learning and matrix decomposition, and I've tried to make it as simple as possible since it's aimed at psychometricians, most of whom have never seen Python. A Daemon object there's only one object in daemon. It's a daemon object, and it has a series of methods. So it loads in data. It can be used to create data as well. And it applies a series of pre-processing steps. Then it computes coordinates, decomposes the matrix. The most important thing is it finds the dimensionality that best describes the data in a very rigorous way, and in such a way that that dimensionality can be enforced on all tests, because that's the only way that you can meet the objectivity requirement, the invariance requirement across students. So just as a quick little demo, I know I should be doing this in IPython, but I'm about 5 years behind the curve here. But so there's this little template script in which I'm writing a sample daemon program right here. Here I'm creating some artificial data. I put it together this afternoon. And I'm taking the same set of persons. There are 1,000 persons. And the first 500, I'm putting the first 500 rows for a set of persons, and then the same set of persons for rows 500 to 1,000, but applying different amounts of random noise to them and randomly missing data. So a given person will not, in fact, have taken the same test. He'll have taken a different mix of tests. And so the main work of it here, I'm creating data. It creates a daemon object. There's data, and then there's the model data, which is the data without the noise added. This noise level of 2 is quite a lot, actually, because the overall range is 5. So about half the range is consumed in noise for each individual score. Then here's the heart of the program right here, this coord thing. It computes coordinates. And it does it by searching for the best dimensionality. Now, in this case, I've set the dimensionality at 17. I know a priori that there are 17 dimensions in this data. And because you can see up here when I built the coordinates, it's got 17 dimensions. And so the goal is to try to find that. I'm already out of time? Okay. It computes, it's going to search for these coordinates, it's going to go in and compute measures out of those, and then we'll see if we can, if I come up with the same measures for the persons. Now I'm going to run it. Now this, while it's running, I want to talk a little bit about this. Okay. All right.
I wanted to talk very briefly about a package that I worked on as part of my PhD work, and that I'm now releasing as open source. I looked around when I started out working on my thesis and saw that there wasn't really much out there in the way of a general purpose open source package for evolutionary computation in Python, which is what I was doing. And so I built my own code, and I'm now in the process of cleaning it up and releasing it. It's still very much in a research state, but I've cleaned up a few things here. Now, I was mainly using evolutionary computation for optimization, so I've exposed an interface that lets you use some of these methods to optimize functions very simply. The name of the package is Pyec, P-Y-E-C, and you can just use easy install to get it. The optimization package is pyec.optimize. So you can import that, and then I've got 7 different optimizers that I've exposed through that interface, and there are others down in the guts of the code that you'd have to do some spelunking to find. The methods that I have there are CMAES, which is develops this multivariate normal that just searches through the space looking for the optimum, and throws down samples, builds a new normal distribution, and gradually shrinks up until it's on the global optimum. Evolutionary annealing is my method. Differential evolution is one of the better methods for optimization, but it can take a little while longer to run. My method actually takes quite a bit of time to run as well. But then I have some of the oldies but goodies like Nelder-Mead. Generating set search is a direct search method. I've got simulated annealing in there, and particle swarm optimization. For a very simple example, suppose we take the function that's just the Euclidean norm in a d-dimensional real space. And then we can, for example, just create our function. Here I have this Euclid norm. And then I can run CMAES on it just by doing pyec.optimize.cmaes, pass it the function, pass it a dimension, and run it if it's going to run at all. I think, well, you can see a result there from earlier. I think the computer is not wanting to run things for me right now. But you can see there it gets, it would actually very quickly get within very close to the true optimum. And so you can run all these different methods in the same way. You just pass in the function dimension. Really simple. Moving along, what we're really interested in with these methods is typically non-smooth optimization. If you want to do convex optimization, you're pretty much just going to use something like conjugate gradient descent. It'll work really well. You can use SciPy's optimization tools and whatnot. For this package, it's designed for more complex functions. So this is Whitley's function, and here you can see it's actually very complex and very multimodal. And outside of this image, this is sort of the critical area. It drops off very low down. As an example, if I were just to import SciPy's fmin and run it here on just a starting point that I just made up, I get a function value of 14, whereas then with these methods that are designed more for these really rough functions, for example, I put in my evolutionary annealing, you can see it found a function value of 1.36. We're doing minimization of this function, by the way. That's the standard thing to be doing. And then the other methods, you can see they also do somewhat better than your standard numerical methods. The catch is that these are random methods. They're not always going to return the same thing. I've got tools in there to let you do constrained optimization as well. You just provide a constraint region, which I can't quite get in there, but in this case it's just a hyperrectangle. You can throw in your own initial distributions. And down in the guts, I've got lots of stuff for evolutionary computation. It's hard to deal with. I'm hoping to clean that up. So if anybody wants to work on evolutionary computation package for Python and help put some of this into a more usable state, please talk to me. I'd love to discuss how that can be done. Thank you.
All right, so this is actually a pretty light thing, so hopefully you'll enjoy it. So this is taking something, neural networks and machine learning, and using it for something totally that it was not designed for, which is generating art. So unlike maybe what you might be familiar with, which are multi-layer perceptron networks, where you've got hidden layers and the signal moves through it and it learns how to approximate some function or do some task, I'm using something called a self-organizing map. This is a grid, an array of neurons that are arranged in some sort of topographic orientation that is preserved throughout the training. It uses a winner-take-all response, which means that an input comes in, you calculate some sort of distance metric to figure out which neuron's weight values closely match the input value, and then you adjust the weights of the neuron to be similar to the weights of the input or the value of the input. This is an example of unsupervised learning. It's used in clustering type of algorithms, knowledge discovery type algorithms. So you can provide an image as an input source. So I was doing work on this for doing some neural networks on GPUs, and I needed a lot of data. And I realized that I could take an image, because an image has, and this one in particular has a couple million pixels in it. Each pixel has 3 values. I can use those. That's nice. And so the nice thing about the SOM is that you can actually represent the state of the network graphically by, in this case, mapping the values of the neurons into RGB values and then drawing images from them. So this is what it looks like as these things evolve. As we present pixels, in this case, you're seeing it in different states after a number of lines of that image have been presented. And it kind of has this weird Petri dish kind of thing going on, it looks like, where the gray is coming in. It starts with at the beginning, it starts with a totally random network. So we just randomize the values, and then we start presenting pixels. And over time, this network actually starts to learn, to some degree, the interface, or the palette of the input image. But it does these kind of weird blobby things, which is kind of interesting. So I've used this to create a number of different images, which I think are kind of cool. And what's really fascinating is the 2 images on the left are from the same source image. But by using different neighborhood kernels for how the neurons respond based on the input, the size of those kernels and the the other parameters that you can tune, such as how strongly they affect things, the radius of the neighborhood, you can get radically different things out. So one thing I did with this is, in addition to running it normally, you can see this running in real time. So here, this is an image I got off of the SciPy website, and we are training the SOM, and you can see this happen where it's just going to run. And so what's kind of neat about this is that you can get these weird abstract textures out of this, which I find is actually kind of a lot of fun, or you just have this kind of really neat screensaver thing that's going on. And basically, again, what's happening is the pixel's coming in, it's finding the closest neighborhood. In this case, we're just doing a Euclidean distance based on the RGB values, and it's then updating the neighborhood weights. This is slow, and especially for large images, because you have to calculate across the entire space, which is why I originally did this on a GPU. But yeah, I think this is kind of fun. Thank you.
Matt Terry, I'd like to say hello to all of the other Matts in the room. There's like 30 of us. Hopefully we'll have more next year. I have a data transfer problem that I think you will find humorous. So you can see up on the screens, I have my colorful fluid dynamics, and then the paper that I want to put this figure into. But the problem is the computers where I do my simulations and the computers where I write my papers are completely different. And normally you would think, no big deal, you just send it over the network, but there's no network connecting them. And you think, well, just send it over wireless. No, there's no wireless. Well, burn it to a CD. They've taken the CD players out. So maybe just stick it on a thumb drive, right? No, we have hot glued all of the USB plugs. So I have a problem. And so I realized my only output device is my printer copier scanner. My only output input device is my printer copier scanner. So I have this really terrible hack to take a NumPy array and cut it into pieces and put it into QR codes that I then print and then scan them back in, and you get your NumPy array back. So I don't entirely recommend this. So there's a bunch of these. If you look up here on the top, this is 1,001 pages. That's 2 reams of paper for a single image for one of the coordinates. But it'll get you through in a pinch. So I just leave you with, this is my conclusion, that this is great and a wonderful hack, and just encourage you all that when you run into really insurmountable problems, there is probably one solution to it that is perfect and inelegant and disgusting, but it'll get you answers in the end. So, thank you.
Is this the mic? Yes. Hi, everyone. I want to talk to all of you for a minute about Numb Focus. The URL for Numb Focus is, as you would expect, numbfocus.org. And Numb Focus is a new effort that we are trying to launch around the community that was spearheaded by Travis Oliphant as a foundation to try to provide a neutral space and a neutral ground where we can try to aggregate resources to support a lot of the work that is done in this community. This community has existed for roughly 10 years maybe, and it has happened, things have happened in a somewhat haphazard way. Nthought has been here since the beginning. Some projects have had funding officially, others leech off grants in not necessarily very sanctified ways, and we're trying to improve upon that by having a foundation where it may be possible, for example, to contact industry and offer a neutral space where industry can contribute, and then those contributions can go back to the specific projects in a more organized way. Officially, these are the terms of our mission statement, but I want to try to explain the broader context. With these resources, if we manage to aggregate them and to obtain them, we will conduct activities such as sponsoring sprints and conferences, providing scholarships, paying for people's time, paying for development of critical features that may be missing, and as I said, trying to raise funds from a number of sources. We have currently one permanent staff member, Leah Holdridge, who is in the back there. Leah, I don't know if you could perhaps raise your hand. There you go. Who works at Continuum, but basically devotes her time to Numb Focus. Leah has been doing all of the necessary work to turn Numb Focus into a 501c3. We've been signing the paperwork today. Currently, the board of directors is consisted of Travis, Perry Greenfield, John Hunter, Jared Millman, and myself, and I think that's it. And we are in the process of basically becoming a proper 501c3 so that we can do this in a tax-deductible way. And we're trying to organize it around a few sort of core projects that are kind of at the very center of all of the things we've been discussing, but we want to build around that a layer of inviting other projects and eventually as many as possible that can benefit from these resources. So we just want to make you all aware of this. There is at numbfocus.org there are links for a discussion mailing list where we would like to involve the community in this aspect of the development, which isn't the code itself, it's not the libraries, it's the rest of the resources that we need for this ecosystem. And this is what I have about Numb Focus, but I also want to add one little link about a BOF that Chris Keys and I are organizing to run at 6:30 to discuss kind of the more federally funded side of things. How do we talk to we know that we don't have any program managers that I know of from any of the federal agencies here, unless one came unannounced. But at least those of you who are in contact with program managers, who have been, or who have been successful at getting federal funding from any of the agencies, I think it would be good if we have just a discussion on ideas about this. So anyone who's interested in that, please come to the BOF at 6:30 down at 109. Thank you.
I'm rebooting, so we'll see if that comes back, but it's not too big of a deal. This morning in his keynote, Professor Bloom used the phrase software carpentry. And in addition to being a really nice euphemism for the work that you do building software tools, it's also an actual organization, an educational organization whose goal is to teach software skills to scientists and engineers, specifically targeting postdocs and graduate students. We go around to institutions running usually 2-day workshops, and we cover things, tools software engineers use, like version control. We teach Python as the language that we as we've said a few times today, kind of the lingua franca of scientific computing. So we teach Python. We teach Shell to people who don't already know that, there are people that don't already know Shell. Totally free that we do this. It's a volunteer organization. So I'll fly around to places and do this. Anthony Skopatz, who you've seen several times in this conference, does this. We have a really big team. And people seem to really like it. So let me show you the page here. So we need help. We can always use more instructors. We need people to raise their hand and say, we want a software carpentry boot camp at my institution in conjunction with your conference or something like that. And if you get in touch with me today, with Greg Wilson, who runs this in Toronto, at the contact information down here at the bottom, we will work with you to set one of these up. You can see if there's already one coming up in your area. We've got a long list here of things coming up. So we need hosters, we need instructors, and we need developers, people who are interested in expanding the curriculum of this. There are a whole bunch of lectures up here currently. These are YouTube videos, voiceover slides that people can go and watch. They're actually pretty useful. Especially for things that you might not have to use very often, like regular expressions and stuff. But we want to change this to something a little more user-friendly and take it out of YouTube videos, use HTML5 to make it so that you can select text right out of the tutorials and things like that. And this gets used in conjunction with the boot camps, right? We do 2 days, and then we do follow-ups online, video cons, where I'll set up a video con, have my IPython notebook there, and run through the basic usage of NumPy, or how to do plots in Matplotlib for people. And so we're looking for more developers to help develop content to change this. We actually, I think Greg sort of wants to move that onto GitHub so people can fork and change that and reuse it. All of this is under a Creative Commons license if you want to reuse it. So if this is something you're interested in, you can talk to me, you can get in touch with Greg directly, but we're always looking for more helpers with this kind of thing. So thank you very much.
Oh, there's one.
Okay.
Let me use my own note, because I know it works.
You're right. Yeah.
No, I'm good. Oh, that's on. Oh, whatever you prefer me to use. I'll go ahead and wear it. I can't, I don't plan on walking around, but I don't want to forget. Okay, so. Okay.
How long did it start? More or less.
5 minutes. Oh, 3 minutes. Cool.
That's not yours, that's their dongle, not yours, Pat?
This is theirs.
That's theirs, so you got your own. Yep.
I decided to go with something I knew that worked.
So I guess it's 20 minutes each, so
That's fine. Yeah, I shouldn't go the full time.
What?
I shouldn't go the whole time. But, yeah, I'll be watching.
Okay, I'd like to welcome everybody to the mini symposium on climate and media.